Okay, so you're going to have to probably solve some problems related to electromagnetic radiation. And so I want to sort of explain to you how to do this. One of the key formulas that you'll need to know is this one here, which is c, which symbolizes the speed of light in a vacuum, which is 3.0 times 10 to the 8 meters per second, is equal to the wavelength of the light wave, which is symbolized by lambda, multiplied by the frequency of the light wave, which is symbolized by nu. And so you're going to be using this formula quite a bit. And so one of the things you can sort of maybe imagine when you look at this formula is that imagine for different waves, this formula will apply. But in each case with the different light waves, c has exactly the same value. So you can sort of predict that if wavelength increases of the waves and that value is going up, then to keep c constant, then what you need to do is you need to take frequency and you need to lower it. And so pretty much this equation shows you that lambda, the wavelength of light waves, must be inversely related to the frequency of these waves. Okay, so I want to go ahead and start doing a practice problem here. And just to sort of exemplify how do you use this formula. It says the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. What is the frequency of this radiation? Okay, so let's go ahead and try solving this problem. Okay, so again, what we're trying to do is we're given a wavelength for a certain light wave, which is the light coming out from a sodium vapor lamp, and that wavelength is 589 nanometers. And we're trying to calculate the frequency of that wave. And so the formula you would use for that is c is equal to lambda nu, where c is equal to the speed of light of all light waves, which is 3.0 times 10 to the 8 meters per second. Wavelength, which you know in this problem, is 589 nanometers, and frequency is what you're trying to find. So let's go ahead and assign variables here, like this. So we know that c is 3.00 times 10 to the 8 meters per second, and this will be given to you on your test. Wavelength, right now we have 589 nanometers, and frequency is what we're trying to find. Okay, so what I'm going to do right now for the next step is just to solve this equation for the variable we want to find, which is frequency. So if I move lambda here onto the other side of the equal sign, here it's in the numerator. When it goes to the other side of the equal sign, it should go in the denominator. So the equation, which is equivalent, is frequency is equal to c, which is the speed of light, divided by wavelength. Okay, so now let's think what would happen if we just took in these numbers and plugged them in and try to get an answer. Could we go ahead and do that right now as it is? Well, you have to be careful about units. So what you can see is that c is 3 times 10 to the 8 meters per second. So you have meters per second in the numerator, but wavelength here is in nanometers. So you would have nanometers in the denominator. So you would have meters and meters per second in the numerator and nanometers in the denominator. So you can't really get those units of length to cancel. We need to do that. So what we need to do is convert nanometers to meters. And then once that's in meters, we can throw that in the equation. The meters will cancel, and we're probably going to be left with an answer in per second. So let's go ahead and try that. So the thing to sort of remember here is the number of meters in a nanometer. So I'm going to write this here. So 1 nanometer, there's not much of a meter in a nanometer, right? So it's going to be 1 times 10 to the negative 9 meters. And so what you can do is you can write out a couple of fractions here. Let me just write 1 nanometer over 1 times 10 to the negative 9 meters. Okay, so what I'm going to do is convert nanometers to meters, and so I'll write times 1 times 10 to the negative 9 meters over 1 nanometer. Okay, and so if we wanted to, we can figure out at this time how many meters is 589 nanometers. And so one way to do that is just multiply these numbers, and I think if you were to go ahead and do that, what you would find is 589 nanometers times 1 times 10 to the negative 9 meters. We should get a 5.89 times 10 to the negative 7 meters. Okay, so far so good. So now at this point, because we have c in meters per second and we have wavelength in meters, you can see we can just go ahead and plug it into the formula because meters will cancel. So let me go ahead and do that. Okay, so at this point what we can do is we can solve this for frequency. So let's just go ahead and plug in numbers. So frequency here is going to be c, the speed of light, divided by the wavelength, which is lambda. So it's going to be equal to 3.00 times 10 to the 8 meters per second divided by wavelength, which is, looks like it's going to be 5.89 times 10 to the negative 7 meters. Okay, so first off, let's just see what's going to happen with units. And so you can see we have meters in the numerator here, cancels out with meters in the denominator here, so they should cancel out. And you're leaving seconds in the denominator of a fraction within the numerator. So what would that be? So if you did this math, 3.00 times 10 to the 8, divided by 5.89 times 10 to the negative 7, you should get 5.09 times 10 to the 14. So let's talk about what the units are going to be. Again, the meters cancels out. The seconds, you can put it in a number of places. You could write it like this, per second, like that. Or you could write it like this, 5.09 times 10 to the 14, and then just use a slash like this and write second here. Or you can write 5.09 times 10 to the 14. If seconds in the denominator, you can write seconds or s for seconds and write negative exponent 1 for that. So let's talk about what the SI units per second would be. So again, just to remind you, when you have a number per second, this is the number of cycles that are passing per second. So this is cycles per second, which you learned is hertz. So the answer could be 5.09 times 10 to the 14 hertz is the answer. Now, there's one other thing I kind of want to point out. There's a slightly different way you can solve the problem, which may be a little bit quicker for you, so I'm going to show you that really fast. So going back to how we dealt with wavelength here, we had 589 nanometers and we had to convert this to meters. And so what we did is we applied a fraction and we got it into meters. Now, there's another way we can use this fraction again, but we can do the math a little bit differently. So what you'll notice here is you have the number 589. What you can do is you can multiply by 1 here and then keep times 10 to the negative 9. And that number should be the same as 5.89 times 10 to the negative 7. So if you wanted to, if you take 589 times this number, it's this, you can write 589 times 10 to the negative 9 meters. So 5.89 times 10 to the negative 7 is equivalent to 589 times 10 to the negative 9. They're exactly the same. It's just that 589 times 10 to the negative 9 is not really good scientific notation. Anyway, if you wanted to, you could solve this problem, but instead of having 5.89 times 10 to the negative 7, you could put in instead 589 times 10 to the negative 9 meters, and you would get exactly the same answer. Okay, so let's move on. Okay, let's do another problem. So an FM radio station broadcasts electromagnetic radiation at a frequency of 103.4 megahertz. Calculate the wavelength of this radiation in meters. Okay. Again, what we have here is a frequency, which is 103.4 megahertz, and we're trying to find a wavelength from that. So this is a form of electromagnetic radiation light, and so therefore you can use the formula that we just learned about that relates frequency and wavelength of light, which is, again, c, which is the speed of light, is equal to the wavelength of light, which is lambda, times the frequency of the light, which is nu. Okay, so let's go ahead and assign variables and see what we have. And so what we have, again, we will know the value of the speed of light that will be given to you. It's 3.00 times 10 to the 8 meters per second. You're trying to find wavelength here. This is what you're trying to find. And we're given a frequency, which is 103.4 megahertz. Okay, so we're going to try to find lambda. And so what we can do is we can take this equation and solve it for lambda. So again, here you take this frequency here in the numerator, when you put it on the other side of the equal sign, it goes in the denominator. So lambda, which is wavelength, should be equal to c, speed of light, over the frequency nu. Okay, so I think you can see maybe at this point we have a bit of a problem. We cannot directly put in these two numbers into this equation and get the right answer. And the reason is the speed of light is in meters per second. Frequency is not in hertz. If it was in hertz, it would be in per second, and you could plug that in. But instead, it is not in hertz. It's in megahertz. So it's not in per second, it's in per million of a second. And so you cannot have meters per second and then divide it by millions of a second and get the answer. So what you'll have to do is convert this megahertz into hertz, because then it'll be in per second and you can plug it into the equation. So you sort of have to figure out how many hertz are in a megahertz. Okay, megahertz, you can imagine that this is going to be a lot of hertz, right? It's going to be a million hertz. So 1 megahertz is equal to 1 times 10 to the 6 hertz. Okay, so what you can do is you can take this megahertz and convert it to hertz like this, times 1 times 10 to the 6 hertz over 1 megahertz. And so let's go ahead and work this out, what it'll be. So megahertz cancels here, and so it's going to be 103.4 times 1 times 10 to the 6, so it's just going to be equal to 103.4 times 10 to the 6 hertz. Okay, now that we have frequency in hertz, it's in per second, right? So let me just write this here. It's 103.4 times 10 to the 6 per second. So I'm going to put a slash here, per second. Then what I can do is, since I know what the speed of light is and we know what the frequency is in per second, then we can solve for wavelength. So wavelength here is equal to 3.00 times 10 to the 8 meters per second over 103.4 times 10 to the 6 per second. And so one of the things you can sort of see now at this point is that the seconds cancels out, and so we should get an answer in meters. And so if you solve this, we're wanting an answer in meters, and I think if you go ahead and do the math, what you'll get is 2.90 meters. Okay, so let's move on. Okay. So one last thing I sort of need to mention about light waves is that you should know two properties that they can undergo. They can undergo something called constructive interference and destructive interference. And so to understand how that happens with light waves, maybe the best thing to do is imagine how that would happen with a water wave. So let's say you have two water waves. Let's say they're in different places on the lake and they're heading toward each other. And let's say they meet at a certain point in the lake, and they meet in such a wave that the crest of one of the waves is exactly on top of the crest from the other wave. And so if the crests are right on top of each other, then it said that these waves are in phase. And what will happen is the crests basically will add up into each other. So let's say you had the first wave with its crest, let's say its amplitude was 1 unit, and let's say the crest of the second wave was 1 unit. You would create a new wave when these crests added together, and the amplitude would be 2 units. And so when you have waves in phase, meaning the crests are really right on top of each other when they meet, they create a larger wave with a bigger crest, and this is called constructive interference. And so one of the things I encourage you to do is to click on that link there and watch the video, and you'll see a guy creating a wave from one end of something called a wave table and a wave from another end of the wave table, and he creates them in such a wave such that the crests meet in the middle of the table, and then they kind of build into each other, and he gets a larger wave in the center of the table. So that's an example of constructive interference. Now the other thing that you should know is that it could be that when you have waves that meet in space, it may not be that the crest of a wave meets exactly with the crest of another wave. Instead, the crest of one wave may meet with a trough of another wave. So when that happens, when you don't have crests meet in phase, if you have a crest of a wave meet, say, with a trough of another wave, then you would say that those two waves are meeting out of phase. So if the crest of the wave meets with the trough of another wave, you add those up like you did before, but basically you have a crest plus a trough. And so when those add up, they completely cancel out. And so you would get no wave coming out of that. And so that process where you have two waves meeting that are out of phase, that you have a crest and a trough meet, so that when they meet, basically the waves cancel each other out. That is called destructive interference. And so again, I have a link there to the same guy with the same light table, and he's creating two waves again, such that they'll be out of phase when they meet in the middle, and what you should see is that those waves will cancel each other out and you're sort of left with nothing after they meet. Okay, well, thank you for listening to that. We will see you next time.